Hello students, we'll start today with the actinoid elements, and the actinoid elements are those which come after actinium, and the elements which come after actinium are 14 elements. Thorium, atomic number 90, and it ends with lawrencium, whose atomic number is 103. Let's see the electronic configuration of actinium and actinoid elements. The general electronic configuration is Rn, radon, it is 5f 1 to 14, 6d 0 to 1, 7s2. So the first element, actinium, 89 atomic number, radon 6d1, 7s2. And all actinoid elements, they exhibit +3 oxidation state. In addition to +3, they exhibit variable oxidation states also. Thorium, whose atomic number is 90, its electronic configuration is Rn 6d2 7s2. Proactinium, 91 is its atomic number, Rn 5f2 61 7s2. Uranium, 92, Rn 5f3 61 7s2. Neptunium, 93, Rn 5f4 61 7s2. Plutonium, 94, Rn 5f6 6d0 7s2. Americium, 95 is its atomic number, Rn 5f7 6d0 7s2. Curium, 96, Rn 5f7 6d1 7s2. Berkelium, 97, Rn 5f9 6d0 7s2. Then is californium, 98, Rn 5f10 6d0 7s2. Einsteinium, 99, Rn 5f11 6d0 7s2. Fermium, 100, Rn 5f12 6d0 7s2. Mendelevium, Rn 5f13 6d0 7s2. Nobelium, 102, radon 5f14 6d0 7s2. And lawrencium is the last element of this actinoid element with atomic number 103, and its electronic configuration is Rn 5f14 6d1 7s2. And from this table, the following points can be noted down. All the actinoids have common 7s2 configuration and variable occupancy of 5f and 6d subshells. The 14 electrons are being added into 5f except in thorium, but filling of 5f continues again after thorium till 5f orbitals are complete at Z equals to 103 lawrencium. The irregularities in the electronic configurations of actinoids, like those of lanthanoids, are related to the stabilities of F0, F7 and F14 configurations. For example, the configurations of AM and CM are radon 5f7 7s2, 6d0 7s2 and radon 5f7 6d1 7s2 respectively. Berkelium also shows an exceptional configuration of radon 5f9 6d0 7s2, which is neither half filled nor completely filled. Though 4f and 5f orbitals have similar shapes, but 5f is less deeply buried than 4f. Hence, 5f electrons can participate in bonding to a very far extent. Since now some isotopes of many of the actinoids are available in good amounts, their chemistry has been studied by tracer techniques. Oxidation states of actinoid elements, as I said, the dominant oxidation state of these elements is +3. It is similar to that of lanthanoid elements. Besides +3 state, actinoids also exhibit an oxidation state of +4. Some actinoids also show higher oxidation states. The maximum oxidation state first increases up to the middle of the series and then decreases. Example, it increases from +4 for thorium to +5, +6, +7 for Pa, U and Neptunium, but decreases in the succeeding elements. The actinoids resemble lanthanoids in having more compounds in +3 state than in the +4 state. However, the compounds in the +3 and +4 state tend to undergo hydrolysis. Further, it may be noted that in case of actinoids, the distribution of oxidation states is so uneven that it is of no use to discuss their chemistry in terms of oxidation states. Then we come to ionic radii and actinoid contraction. As we have seen the lanthanoid contraction in the last video, here we'll see the actinoid contraction. And the actinoids, they also show actinoid contraction due to poor shielding effect of the 5f electrons. Their lanthanoid showed lanthanoid contraction due to poor shielding of 4f electrons. Here, actinoid contraction is seen due to poor shielding of 5f electrons. As a result, the radii of the atoms or ions of these metals decrease regularly across the series. The contraction is greater from element to element in this series due to poorer shielding effect by 5f electrons. And this is because 5f orbitals extend in space beyond 6s and 6p orbitals, whereas 4f orbitals are buried deep inside the atom. So you can see the ionic radii of actinoid elements here also. It is ionic radii is decreasing. So the decrease in the ionic radius of the elements with that of the ionic radii as well as the atomic radii of the elements of actinoids with respect to that of increase in atomic number is called as actinoid contraction. Let's come to the general characteristic features of actinoids. Like lanthanoids, actinoids are metals with silvery appearance. Structural variability, as they have much greater irregularities in their metallic radii than lanthanoids, they show great structural variability. Color, usually these metals are silvery white. However, actinoid cations are generally colored. The color of the cation depends upon the number of 5f electrons. The cations containing no 5f electron or having 7 5f electron, that is exactly half filled F subshell, are colorless. The cations containing 2 to 6 electrons in the 5f subshell are colored both in crystalline as well as in aqueous solutions. The color arises due to FF transition. Example, AC3+, 5F0 is colorless. U3+, 5F3 is red. NP3+, 5F4 is blue. PU3+, 5F5 is violet. AM3+, 5F6 is pink. CM3+, 5F7 is colorless. Thorium in +3 state, 5F0 colorless, and so on. Melting and boiling points. The actinoids, like lanthanoids, have high melting and boiling points. However, they do not show any regular trend with rise in atomic number. Density. All the actinoids except thorium and americium have high densities. Ionization enthalpies. Actinoids have lower ionization enthalpies in comparison to lanthanoids because 5F is less penetrating than 4F and hence is more effectively shielded from the nuclear charge. Electropositive character. All the known actinoid metals are highly electropositive. They resemble the elements of lanthanoid series in this respect. Magnetic behavior. Like lanthanoids, the actinoid elements are strongly paramagnetic. The variation in magnetic susceptibility of actinoids with the increasing number of unpaired electrons is similar to that of lanthanoids, but the values are higher for the actinoids than for the lanthanoids. Reducing agent, all actinoids are strong reducing agents. Radioactivity, all the actinoid elements are radioactive in nature. First few members have relatively long half-lives. However, the remaining members have half-lives ranging from a few days to few minutes. Example, for Laurentium, the half-life period is 3 minutes. Complex formation. Actinoids have higher tendency to form complexes than lanthanoids. It is due to higher charge and smaller size of their ions. Most of the complexes are formed by halides of actinoids with alkali metal halides. Chemical behavior. They are highly reactive metals, especially in the finely divided state. A few properties are given below. They react with boiling water to give a mixture of oxide and hydride. They combine with most of the nonmetals at moderate temperature. All these metals are attacked by hydrochloric acid, but the effect of nitric acid is very small due to the formation of a protective oxide layer on their surface. Alkalis have no action on them. Let's see the uses of actinoids. The three most important actinoids which find uses as such or in the form of the compounds are thorium, uranium, and plutonium. A few uses of these elements are as follows. Uses of thorium, it is used in atomic reactors and in the treatment of cancer. Its salts are used in making incandescent gas mantles. Uses of uranium, it is used as a nuclear fuel. Its salts are used in glass industry for imparting green color, textile industry, ceramic industry, and in medicines. Uses of plutonium, it is used as a fuel for atomic reactors as well as for making atomic bombs. Let's see the comparison of lanthanoids and actinoids. Similarities, as both lanthanoids and actinoids involve filling of f orbitals there, they show similarities in many respects, that is discussed as follows. Both show mainly an oxidation state of +3. So +3 oxidation state is common both for lanthanoids as well as actinoids. Both are electropositive and are very reactive. Both exhibit magnetic and spectral properties. Actinoids exhibit actinoid contraction like lanthanoid contraction shown by lanthanoids. Let's look at the differences. They show differences in some of the characteristics as follows. Look at the difference between lanthanoids and actinoids. The first difference is, besides +3 oxidation state, they show +2 and +4 oxidation states only in few cases. Whereas in actinoids, besides +3 oxidation state, they show higher oxidation states of +4, +5, +6, and +7 also. Most of their ions are colorless in lanthanoids, whereas in actinoids, most of their ions are colored. The lanthanoids have tendency towards complex formation. They have less tendency towards complex formation, whereas actinoids have greater tendency towards complex formation. Lanthanum oxides and hydroxides are less basic, and actinoid oxides and hydroxides are more basic. Lanthanoids do not form oxocations, whereas actinoids form oxocations, example UO2, 2+, PuO2, 2+, etc. Except promethium in lanthanoids, they are non-radioactive. Only promethium is radioactive in nature. Rest all are non-radioactive, whereas actinoid elements all are radioactive in nature. Lanthanoids, the magnetic properties can be explained very easily, whereas in actinoids, the magnetic properties cannot be explained easily as they are more complex in nature. So these are the differences between lanthanoids and actinoids, and we finish with this F block elements here. Thank you, children, and have a nice day.